So, good morning, everyone. Thanks for coming. So, this is joint work with my new students, Dimitri, Joshua, and Vinay. And what we are interested is how to enable POMDP to be practical for problems where there are changes in the model. So I guess it's going to be a bit different than the previous session where there's a lot of grasping, but what I'm trying to talk about is more on the tools that you can use, for instance, for grasping. And considering this workshop and session we have before, I think I don't need to talk much about why we want to do uncertainty planning and things like that. But just one thing, I guess the bigger question is how do we make robots be able to make effective decisions despite of the various uncertainties it has, from the control errors that might be caused by external disturbances, like in the underwater vehicles or surface vehicles, then sensing errors, and then also because of the limited information and its understanding about the environment. So, well, this problem is not exactly that new. It's actually been worked on in many different areas, and one of it from the decision theory actually gives us a nice mathematically principled framework for dealing with this kind of problems, which is called the partially observable Markov decision process, where the key is that, well, because of all this uncertainty, we might not know the state of the system, so maybe we just represent all this uncertainty with probability distribution, and then we can infer what is the best action with respect to this distribution rather than with respect to a particular state. So I'll talk a little bit more on the POMDP, unless if you get bored with this, then just let me know. I'll just skip it. So I think because I will talk about how we can adapt with respect to changes in the model, I'll talk a little bit on what exactly by model that I'm going to talk here. So it's basically the POMDP model where the main components is the state space. So this is a very simple example where just a robot navigating in a grid cell, but nowadays we can deal with continuous state space, but this is easier to talk with. Sorry. So it consists of state space, where the robot might be in this case, and then action space, the set of possible actions that the robot can do. In this case, we are still dealing with discrete action space. There are ways, well, just very new ways on dealing with continuous action space, but usually what we do in there is that we restrict the kind of problem we can deal with, and there's still a lot of things that need to be done there. Then observation space, nowadays we can also deal with continuous observation space. And then, so observation space is basically the set of observation you might be able to see. And now to represent this uncertainty, these errors in controller, for instance, we represent it as conditional probability in the transition function. And then for the sensing error, we represent it as observation function, again, as a conditional probability. And in POMDP, we'll try to maximize some reward function. So this is basically the objective function we want to maximize. The main thing here is that because of the errors and limited information we have, then in general, we don't actually know the states that we are in. And so we try to plan or infer everything with respect to belief, which is just a distribution over the set of possible states. So it's just, in this case, it's just very simple distributions, discrete distributions. So then the main goal here is that we want to find a policy which is nothing more than the mapping from beliefs to actions, so from distributions over the states to actions. And once we have that, well, we can treat the policy as just a feedback controller. So we will estimate what is the state that the robot is in with representing it as distribution. So this is the belief estimate. And then based on what belief we are in, we can figure out from the policy what is the best action to perform. And then we can update our understanding of where we are using the action we have performed and also the observation we get from the environment. And that's it. That's all about POMDP, but the difficulty is always generating this policy, and it's been shown to be computationally intractable. in particular is actually exponential with respect to the number of states, the number of observations, and doubly exponential with the number of planning horizon we have. Well, that seems like very daunting, but there's been a lot of progress recently, and it started with the sampling-based approach in 2003, where basically Joel Pinel realized that we don't actually need to plan with respect to the entire belief space. So we basically only need to plan with a set of representative beliefs, which basically means we are trading off optimality with approximate optimality for speed. And that helps a lot, that from before this, we can only solve 12 states problem, and it takes days. And now it can, in 2003, it can solve 870 states problem. But the problem is it still takes 50 hours, which is somewhat unreasonable, especially because in many robotics problems, we have much more state space, much more states, much more actions, much more observation space than this benchmark problem. I think I forgot to mention this benchmark problem is basically a target finding problem in a grid environment. But since then, there's been a lot of progress over the past 10 years. So now we can solve that problem in just 6 seconds. It's no longer 50 hours, so it's good. And now we can also solve much more complicated problem, including cooperative navigation between a surface vehicle and underwater vehicle after we plan for around 10 minutes. And we can also start solving problems with continuous state space. In here, actually, we have 15-dimensional continuous state space. And the collision avoidance, mid-air collision avoidance problem of aircraft, which has 10-dimensional state space problem, again, continuous state space. And then recently, actually, it's been used for grasping very small objects by Horowitz and Budryk. So there seems to be quite some interesting progress, and hopefully things can move on further. And the problem here is that although all are great, but most of these algorithms, most of the solvers actually assume that we know the POMDP model a priori, and during runtime, that model will not change. So, so there are actually ways to handle these changes. So I would like if I say there's no way we can deal with this. So there has been quite a number of works. 2 types of approaches have been proposed. One is that you can hedge over all possibilities, which means that all the uncertainties becomes part of the POMDP state variables, because after all is uncertainty, and you can always make bigger and bigger POMDP problems and then try to solve it. But what you end up with is usually a very huge problem, and usually we can solve this by restricting the type of POMDP we are dealing with, either restricting it to just the Gaussian distribution, for instance, or maybe restricting it to a particular type of problems where there are many fully observed states in a problem. Then another type is online POMDP solvers. There's also been quite a number of work on there. And most of these solvers basically do a replanning at each time step. And usually they do this from scratch, which means that they automatically handle changes. But it seems to me is quite a waste of time if every time step you actually throw away whatever you have calculated before and then start planning from zero again. So what I'm trying to do is that, of course, I want to keep the online part, but I want to also be able to hedge over some of the possible changes, in the sense that in this kind of approach, usually what people do when we have no information whatsoever about the environment is that we say, okay, well, we can always assume this as a part of the state variables and give a uniform initial distribution, for instance. But it seems a bit unreasonable to keep making everything to be uniform distribution without additional information. So maybe it's better if we really don't know, then don't put that as part of the POMDP. But what we are uncertain and have some initial model, we can put that as part of the POMDP problems, and then we can refine over time. But what that means is that we need to be able to adapt the POMDP policy that we have calculated so far, and we need to be able to do that fast during runtime when we see things are changing, which then implies the POMDP model changes. We need to be able to then adapt our POMDP policy. So the problem is, well, the changes are usually seen in the state space. So we see there's additional obstacle, we see some of the object moves, but our policy is actually a mapping from beliefs, which is distribution over states, to actions. So there's sort of a disconnect between the two. But if we go back a little bit to how we can represent stochastic processes, there's actually two different way of representing stochastic process, which is sequence of distributions indexed by time, and then the other is by sampling sample paths. And in POMDP, most of the solvers do a search using this representation, which is sequence of distributions. So if you're familiar, you usually have a sequence of beliefs or representing it as belief trees. Then sample paths has not been used that much. There are some solvers that use this, but the way they use that is only for an intermediate result, and then after a while, after one step, they actually represent the entire system as, again, sequence of distribution. So basically, they lose the information of which state in one time step connects to which other state in the other time step. So this is what we are trying to maintain, because this information of how the states connected to each other are actually going to help us identify which part of the policy needs to be changed, and so allow us to change the policy locally and doing it fast. So this is a very simple idea. So we propose adaptive belief tree, which combines the belief tree representation, which is nothing more than a tree where the nodes are beliefs, so it's distribution over states. And then the edges is basically a sequence of one action and one observation. And then we have another belief. And combined with that is the set of sample paths. So basically, we represent the beliefs with particles, for instance, and then each of these particles, we have a path from one particle connecting to all the way down into the particles that corresponds to this node at the leaf of the belief tree. And we have the correspondence between them in the sense that each of the sample paths we have in the state, sorry, I think I need to back up. The sample path we have is actually a sequence of state, action, observation, and then state, action, observation. And so this sample path will actually, each of the sample path corresponds to a path in the belief tree. And so if we can see there are changes in our state space, we can easily identify which part of the sample paths are affected. And then from here, we can quickly map it to the belief tree. And from here, we can do the changes we need. And so the policy now is encoded in the belief tree. So with respect to a particular belief, what is the best action to perform in this tree? Okay, so one thing that we need to change is how do we compute the value, because usually we compute the value with respect to expectation over the states in a particular belief. In terms of sample paths, it's actually very easy. All we need to do is that we need to calculate the total reward we will get along a particular sample path, and then the average of this will actually approximate the actual value that we want to calculate. Of course, given a particular sampling strategy. So I'm glossing over some of the details computation, but a certain sampling strategy will allow us to have this converge to the actual value of the beliefs. So now that we have this representation, well, we can use this for offline computation. Then we just generate the policy in this representation, in the adaptive belief tree representation. And then during running time, we can either refine the policy that we have if there's no changes, but if there's changes, then we can actually identify which part of the beliefs needs to be which part of the policy needs to be modified. So we can do this quite simply, that for computing the policy or for refining the policy, we can sample a particular state in a belief. For instance, this is the current belief that we are in. And then we just generate a sample path using our generative model, for instance. And based on that, using the action, matching the action and the observation here, we can correspond this particular sample path with a particular path in the belief tree. And that's it, basically. So very simple. And the tricky part is how do we select actions and how do we select observation. So when we select the actions, at the moment we use UCB1 because it actually guarantees that it can be close to the optimal solution. Basically, it minimizes the regret of not choosing the best action. And for choosing the observation, at the moment we are sampling from the observation function, but that can be improved much more by using smarter sampling strategies. For instance, if we can calculate a rough upper and lower bound, we can use the difference between the upper and lower bound to actually help sample the right part of the tree. And the association is quite simple as well. So that's it. Now, how do we modify the policy online? So, well, one thing is we need to represent these sample paths, basically the sequence of states, action, observation, in particular the states, in a nice data structure. We are using the spatial data structure so that we can easily access which part of the states has been affected by changes in the system, the environment, like the addition of obstacles or things like that. And from there, we can easily identify which part of these states are affected, and therefore we can also identify which sample paths are affected. And because we have a correspondence from these sample paths to the part of the belief tree, in particular with which part of the beliefs, we can easily map that, map that as well. So that's the idea. And suppose we know that this has changed, then we can use, we can revise this path using any available methods that people have found for modifying trajectories. There you go, and that's it. So that's it. So it's very simple. And then, so is it converging to the optimal policy? Well, apparently yes, but it is convergence in probability to the optimal policy of the current POMDP model. So if the POMDP model changes, then it needs to be refined. The policy needs to be refined, and so it can be optimal, converge to optimality with that particular POMDP model. So we have since implemented the software as well as a toolkit. So it implements this algorithm. It is online. It is any time. And then we start by computing offline policy, the initial adaptive belief tree. And then we refine the policy during runtime and can modify the policy based on the changes in the model. And then one other thing is that we provide interface with both command line and also ROS and VREP. So we've done some benchmark result. We compare it with POMCP, which is considered as one of the fastest online POMDP planner today. And these are the common benchmark problems in POMDP. So this is the result that we got after 1 second computation time per step. And and so basically, we can significantly outperform the POMCP. And then, how about when we have changes? These are the results when our POMDP model actually changes over time. And we also try to see how fast can we actually do with some other problems, for instance, some navigation problems. So this problem has almost 2 million states. And then we run this. We have changed. We initially come for the robot starts from here, either here or here, and it should reach the goal, but it doesn't actually know that there are obstacles here in the beginning, and it also doesn't know that there are some places that it should not go in the beginning. And over time, it figures out that there are additional obstacles here, and also there are places it doesn't want to go. These are the time when the robot starts to know, and so at that time, the model changes, and it can actually adapt the policy as well. So again, these are the results comparing with POMCP. Similarly, in here is a target funding where the target is following this path with some probability of staying longer in some of these regions. You can think of this as a home care problem where an elderly person, for instance, might stay longer in their bedroom or places like that. And again, we have changes in the sense in the movement of the person. So actually, this sorry. I don't think I've shown it here, but the path that the person is moving is actually changing over time. So like this W places where the person may stay longer is just added recently. And again, that's the result. So similarly, in here, the robot needs to actually follow the person so that it can help the person at the right time. So yeah, so and then as I mentioned, this toolkit has interface with ROS and VREP. So this is an example of how the tech benchmark with a larger environment, we can change the environment on the fly, and it can actually replan on the fly as well with respect to the new model that we have. Right. And similarly, we can start from an environment where we don't know the environment map, and we can update our understanding about the environment and on the fly change the policy that the robot is using as well. Okay. So basically, that's it. So I guess you can forget whatever I said before, but just one thing is that, so by maintaining both stochastic process representation, both the sample paths and the beliefs, the sequence of distributions, we can actually efficiently adapt the POMDP policy online according to the changes in the model. And we have implemented it as a toolkit with interface to ROS and VREP. So you're welcome to try. So I know this is nothing to do with grasping, but hopefully the tool that we provide here can be used in grasping as some of the previous tools have been used. So that's it.
Thanks, Hannah.
Thanks. Yep.
Can you speculate on how your tool can be used for grasping?
Yeah, sure. So usually, when we have a grasping problem, for instance, we might, I'm pretty sure you know this, sometimes when we try to grasp, we are not actually giving it enough force, and you actually move the object you want to grasp, right? So at the moment, you try to model all the possible grasping angles, for instance, and well, there are several ways you can model this in POMDP. You can either build a different POMDP model for the different type of grasping and then combine them. Basically, there are all sort of way. But what I'm proposing here is that maybe what you can do is that even though in the beginning you don't model that other possibilities of the possible movement your object might have, you can actually, as you get additional observation, you can modify your model and then adapt your policy online for grasping with respect to the current configuration of the object.
What about shape variation?
Sorry.
Shape variation in the object that's being grasped, or sort of online
Yep.
discovering the shape of the object?
Yep. It can be so. So one of the things is that that is okay. I know it's a bit different, but you can think of that as trying to map the environment. So this is actually an example where we can start with unknown environment map, and we build the map, and then over time we actually improve our policy and change it as we understand the environment better.
What I was kind of thinking during your talk was the contrast between Shevin's work and yours. So I don't know if you saw all that
Yep.
planner.
Right.
And if you can find yourself one step look ahead, then there was this optimality.
Right. Right. So.
And now you're multi-steps.
Yep.
You know, and you're
Yep.
paying a price for, you've got better outcomes.
Right.
You're paying a price for that.
Yes.
What, you know,
So.
when would you want to use these different methods?
So it really depends on the problem you have, right? So for instance, Gavin's algorithms will work assuming that your problem actually satisfies the submodularity, the adaptive submodularity constraint. So in this in the algorithm I propose, we don't actually need this requirement anymore. So of course, if your problem actually satisfies the adaptive submodularity, I would suggest use this method because I mean, why do you want to work harder for if your problem does not can be satisfied?
Okay, we drill down a little deeper and say, like, I know it has to satisfy that constraint. So what does that mean for the problem?
Sure. So for example, here you're looking at the card and it's kind of moving around, right? And so it's kind of very local. So all your actions are kind of like the card's here right now. I can go in any of these directions. And that is something where I feel like you would really need to kind of trace the whole tree down because you're not going to satisfy the submodularity in this case, and you're going to be horrendous if you're greedy. You'll never like go all the way to the left necessarily if that's where you need to go.
Right. So in your case, the hand always went back to the beginning.
It didn't always go back to the beginning, but that's kind of an even more basic approach. I think I take a set and it's a global set, so we sample a big set from the beginning and you kind of are just selecting from that set. Whereas you could think of a case where you are just looking at where you are now and being able to move kind of in any cardinal direction. That's kind of the contrast. Yeah.
But you know, when you think of submodularity, I think of diminishing return.
Yeah.
So I'm just wondering, what's the intuition that would distinguish this problem up here versus your problem in that?
They both have diminishing returns in some sense, in that the information you're gathering, kind of once you gather some information, you get fewer.
Well,
More than
yeah.
that, you need basically if you want to be to satisfy some modularity, one way is think of it as a unit. But also you should never be able to set up a future action. Right? Whereas here, if you look at this problem, you can always set up a future action. You can move in a particular way such that the reward of future action becomes lower. Whereas with our problem,
So I think one thing.
actually set up a future action, and that like really curtails your search. That uses the adaptive.
So one thing to note as well is that yes, we for infinite horizon POMDP we have the discount factor, but that does not imply that it is submodular. But because we can actually have a very big reward at far away time step, and therefore we need to plan for longer time.